Good morning to all. Sorry. Good evening to all. So myself Chinnaswamy Naik. So today we are going to discuss about week 5 sessions of environmental remediation of contaminated site course. And then after that we'll just briefly discuss the overview of week 5 sessions, and then we'll solve previous year questions. Good evening, Nirupa. Am I audible? Nirupa, am I audible? So today we are going to discuss briefly about week 5 sessions of environmental remediation of contaminated site course. We'll just discuss the content of the week 5 session briefly, and then we'll move to the previous year week 5 assignment. Okay. So in the course we are going to discuss about environmental remediation of contaminated site, and course instructor of this course is Dr. Banu Prakash Velanki. And myself, I am S.V. Chinnaswamy Naik, a PMRF scholar from IIT Roorkee. So without any further delay, we are going to start just overview of week by sessions in the NPTEL course. So what course instructor taught in the week 5 session. So coming to the first in week 5, here it is in week 4 also we are going to we discuss a lot about PRBs. So that is permeable reactive barriers. Again in week 5 it's week 4 itself we discuss a case study about Huta in USA. Again here we are going to discuss in week 5 also we discuss briefly about a case study Huta. So in Huta, a contaminated site which have various contaminants including uranium. So in this week 5 session we are mainly focusing on contaminate uranium contaminants. So yeah, so in week 5 content we are going to discuss about uranium concentration, how to remediate the site which is contaminated with uranium, and their characteristics and their changes in their different medias we can use it for to remediate the uranium contaminated site, and their experiment results, and mainly the batch test and column test. And after that with the main changes in the uh, membrane, whatever the reactive media we prepared, changes in that and to the their effect on results. So everything we'll be going to discuss today. So then uranium desorption results. So we discuss once you install the membrane PRB, that is reactive media, which can be prepared with different materials like phosphates, zero valent iron phosphates, and AFOs. So whatever the PRB we install in the contaminated site, once the groundwater pass through it, so after few days or few years, the whatever the reactive sites are there in the media, it will going to saturated, means most of the reactive sites are blocked by the contaminants, and very At this situation, what will happen? Whatever the contaminants coming through, flowing through this PRB will again up. There is no treatment. There is no treatment of contaminants because there is very less or no availability of reactive sites in the barrier. So after, in this situation, what will happen? Once the reactive complete blockage of reactive sites, what will happen? The desorption will take place because of complete reactive media is blocked with active, there is no active sites, and because of the precipitation. So what will happen? These pores will get again blocked, and very micro or mesopores will be there. In this situation, what will happen? There will be a drastic rise in hydraulic conductivity, and because of that, some portion of uranium, whatever the uranium treated on the media will be uh, desorption will take place because of those very small colloids, in the form of very small colloids. So we studied about uranium desorption results in the big 5 session, and then different reactive medias we can use it for to remediate the contaminated site, which mainly uranium contaminated site. So here we have with more different number of different types of reactive media, but mainly here focusing on phosphates and zero valent iron. Again in week 5, week 4, week 3 session onwards, we are discussing about zero valent iron, so that is Fe naught, right? So and then amorphous ferric dihydroxides. So these are the main three materials which are particularly used for remediating the uranium contaminants. Okay, and then mainly if you see their mechanisms of this reactive media. So for phosphate, the mechanism for removing this uranium contaminant is the precipitation, because what will happen in the phosphates? So precipitation of insoluble uranyl phosphates phase. Generally, the formula I will write. I am writing this formula for uranyl phosphate, chemical formula. So this is the uranyl phosphate. So what will happen? The precipitation will take place in the case of phosphate reactive media, but when it comes to the zero valent iron, so what will happen? Here reduction plus precipitation will take place. We already well known about zero valent iron reactive media. So because it is act as a zero valent iron, act as a reducing agent. So because of the, what will happen? It will transfer it into Fe2 plus, and again Fe2 plus will transfer it into Fe3 plus, reduced into Fe3 plus, so this Fe3 plus is the insoluble in water, so it will, generally it is a precipitate, so insoluble in water, it can be easily removed by the media, reactive media, that is zero valent iron. So and coming to the AFO nothing, AFO means it is amorphous ferric dihydroxide, so amorphous ferric dihydroxide, but the mechanism for AFO is only adsorption. So in reactive media, so PO4 is only in PO4 media, there is only one mechanism, that is precipitation, and then zero valent iron, both reduction and precipitation, and then in coming to the AFOs, that is amorphous ferric dihydroxide, the mechanism is only desorption. So by desorption to the iron dihydroxide sulfate. So then we in week 5 again course instructor what taught. Yes, hydroxide, yes. So then course instructor were taught about both batch and column test. So how we will decide whether particular reactive media will suitable for remediating the site which is contaminated with uranium. So we'll before installing this reactive media into the field, we'll do some test in the laboratory. Generally those are two kind of test we do. One is batch test, it is a closed system, in the closed system, and one second one is the column test. So we'll conduct these both batch test and column test with different available materials, and with very small scale, and then based on the results of the different material, then we'll choose the only few materials based on the results which is giving more removal efficiency. Based on their performance, we'll choose one or two or three materials, and then we'll do these three whatever the materials which is giving best results, we'll pick these materials and we'll use it for the installing in the field conditions. So these are the tests we discussed. So in column test, in coming to the batch test. So batch test, we can discuss about like how much uranium will just in batch state it is continuous. So we'll place the one material that is reactive media, and then we'll put whatever the uranium known concentration of uranium solution, and then we'll just mix it, we'll try to contact with this material, and then for like stirring in the batch. So what will happen after few minutes or few hours or few days, what will happen, whatever the known concentration will be taken by this media which is there in batch reactor, and then because of the reaction happen, the uranium known concentration of uranium will take reaction with this reactive media, and then what will happen, the reduction in concentration will observe the reduction of concentration of, for suppose initial concentration will be 10 ppm, and then after one day we may observe the concentration of the solution will be around 5 6 like. So what will happen, we'll just observe the how much concentration of uranium will be removed with in the reactor with help of this material. So whatever the material we use for to remove the uranium, whether it may be phosphates or zero valent iron or AFOs, so that is amorphous ferric oxyhydroxide. Okay, so we'll then based on the results we'll calculate via the removal efficiency, and we analyze the results. And then column test also similarly like this only, but in column test what you will get, will observe the breakthrough. So for suppose, so initially the uranium concentration you can say here. So in the time, if you say, if you consider it in time, so in the beginning the removal efficiency will be, uranium concentration will be decreased completely, and then after over the period of time whatever the active sites will be, the most of the active sites and the reactive media will be blocked, and there is a sudden rise in concentration, and then again it reaches to the original concentration, initial concentration after some time. So this is, we call it as a breakthrough. So this curve we call it breakthrough. So we'll observe this breakthrough concentration in the column test. And then release of uranium from the bore char column and uranium effluent concentration from the column experiments. So we, course instructor, discussed uh, different concentration levels and their removal efficiency with respect to different reactive media available. So with respect to column studies and batch studies we discussed. And then factors considered in the evaluating the materials. So we not only consider only the performance of the reactive media, I mean only, not only just removal efficiency, I can say removal, uranium removal performance, not only the uranium removal performance, we will consider other factor also, such as their availability, the material availability, whether it is available, easily available or not, and next the cost of that particular material, and then whatever the reactive media we are placing, installing in the field, that should be more permeable than the surrounding soil strata. Otherwise what will happen, if the reactive media is less permeable than surrounding strata, what will happen, the liquid will, the flow will go away from the reactive media where there is more permeability. So we should make sure that the reactive media should be more permeable than the surrounding soil strata. For that what we can do, generally while installing the PRPs in the field condition, will provide a thick layer of gravel. A thick gravel layer will provide, because gravel have more permeable than the soil. So because of that what will happen, the permeable water will flow towards the PRPs. So that we can do. And then structural strength. So again, so when water is flowing through this PRP, so because of their different velocities of flow path will take place with different velocities. uh, as pore size decreases, the flow velocity will be rises. Because of this rise in velocity, there will be a chances of damaging the structure of the PRP. So because of, so that we have to choose the material such a way that it should resist the any impact from the flow. Mainly again, not only with the flow, again this once we install the PRBs under the soil layer, so what will happen, we should make sure that whatever the crushing or compactive strength which is coming from the above ground, it should resist to the material, PRP material, whatever the PRBs we are installed inside the soil, it should resist to the compactive strength coming from the above ground. And then extent and rate and duration of UV removal. So how much extent of UV is it can remove, and at what rate it can be removed, at what rate uranium can be removed, and again how much time will it take to remove the uranium, and how much time, till what time it can continues to remove the uranium. So most of the cases we see that this, if you consider these three material, zero valent iron can remove uranium till some decades, 10 years I can say. But when it comes to the phosphates or AFOs, the removal of uranium will be around 1 or 2 years, maybe in months. Because what will happening, because there is a active sites blacking of lack of active sites. So within very short period of time, the active sites are completely blocking. So so that we have to choose a material based on the concentration of contaminated site. We have to choose a material such a way that it can remove the uranium over a longer period of time. So extent, rate and duration of UV removal we have to consider, and then mobility. So whatever the no, it is not exactly 10 decades. I am saying compared to phosphates and AFOs, it will be much better. So already course instructor discussed with the help of graph. So zero valent iron will give more removal. It comes very long. It continues to remove uranium for over a longer period of time compared to AFOs, and yeah. So there is no fixed time like 10 years like that, but it will come around like more than 10 years, I can say around 10 years or more than 10 years, you can say. Yeah, but for in uranium removal, for uranium removal, zero valent iron shows best removal efficiency. So that part compared to these two AFOs and PO4s, phosphates. And then mobility. So what whenever when the flow is taking place through this membrane, so whatever the material, it should not break and it should not flow through the whatever flow coming from the upstream. So we should make sure that it indirectly it is representing that strength. If the material is more strength, it won't mobile easily. So because the tendency for the material to remove with the groundwater, so the tendency for A force to form the colloids, but compared to C, A force, but whatever AFOs, that is amorphous ferric oxyhydroxide. So what they are saying, so AFOs are tendency to form a colloids. What does it mean? So if you install the PRB, which is made up of AFOs, what will happen when the water flows through these PRBs? What will happen? Small particles will break it from the PRB, and it will mix with water, and then it will flow along with the groundwater. So because of because of their structural integrity of the AFOs, so colloidal particles are flowing with the groundwater. So because compared to AFOs, we have zero valent iron has more tendency to resist this mobility. And then second factor, another factor we have to consider is potential for re-release of uranium. Whether, for suppose I placed zero valent iron PRB, I installed zero valent iron PRB. So whatever the contaminants coming through this membrane, so it will react with these reactive sites, and then it will precipitate or reduce, or it will adsorb depending on the material. So in case of zero valent iron, what will happen? Adsorption will take place and then precipitation. So after few years, what will happen? All the active sites of the zero valent iron PRB will be blocked, and so completed active sites will be completed or minimal reduced. So what will happen in this case? So whatever the water coming through this PRP, these precipitates will flow along with the these blocked precipitates will flow along with the groundwater. So yeah, because of this concentration gradient, uh, we will experience effluent. Whatever the water coming to groundwater coming through effluent, we'll see the concentration rise of uranium, or uranium which is coming from downstream. Exactly the same whatever the concentration present uranium at downstream, let's suppose 10, again upstream also uranium concentration will be 10, around 10. So what does it mean? There is no active sites to treat this uranium concentration. So we have to consider that material, we have to choose the material such a way that before installing this PRB, we should know about their re-release capacity of the contaminant. And then possible detrimental effect on groundwater quality such as pH change and release of iron and phosphates. So again, so as per water quality standards, whatever the water coming ground contaminated groundwater coming at upstream level, so the pH will be different, and then water which is same groundwater, contaminated groundwater, or we can say same after treating the contaminated groundwater which is coming at downstream, will be the pH will be different. So we have to make sure that whatever the pH which is coming at downstream should meet the what standards given by Bureau of India. So we should check the choose a material such a way that we can maintain these properties of groundwater such as pH or release of other iron. If, for suppose if you use the zero valent iron, we have to make sure that whether the precipitated irons will is uh, coming to the effluents or not. So again, similarly, if we use phosphates, again phosphates is coming at downstream or not, we have to check, so to maintain the groundwater quality standards. And then batch test and column test conclusions and results. So already by seeing the different results with the help of graph, we can conclude that like which material, which PRP material, which material we can choose for PRP, and what this particular PRB will be best for to treat particular contaminant. We can just give conclusion. So in conclusion part, we discuss both in both batch and column studies. Uptake test indicate that bone meal and bone meal and bone char hepatitis would be more effective on per gram basis of the removal of uranium. So we have, so for suppose material, whatever the material we are choosing for PRBs, here on the basis of column test results, column and batch test results, they are concluding that so PRB which is prepared with bone meal and bone charcoal. Bone charcoal nothing but after treating after doing some thermal treatment to the bones, whatever the coal we are getting, that is we used to call it as a charcoal. So that is bone charcoal. So the bone charcoal and bone meal material have more effective for removing the uranium because of its small particle size, and the bone charcoal powder also suffers from the need to dilute with coarse materials and may be transported out of the PRP. So what they're saying, so as because of their less particle size, what will happen, the permeability will be, sorry, so because of the less particle size, what will happen, the surface area of the particular PRBs will be higher. So because of that, the hydraulic conductivity of the particular media will be less, so that we can provide the oh, sorry. So because of the less particle size, what will happen, this smaller particle size will pass s sorry yeah, more surface area for yeah, of course smaller particle will have more surface area to react with the particular contaminant. But what will happen at the same time, what will happen if there is a particle size is small, whatever the media we prepared with particular smaller particle, so what will happen when flow is taking place through this media, what will happen, because of their small size and less density, it there is chances of the small particle flow along with this flow, groundwater, contaminated groundwater. So because of the how we because of this how we have to prepare this this membrane PRBs is by introducing this small particle with larger particles. So if you combine together this by if you fabricate this PRB combine together with smaller particle and bigger particle, there is a less chances of escaping the smaller particle through the flow. So there is no transport of PRB colloids. Similarly, large hydraulic conductivity of pelletized bone char phosphate allow it to use in the PRB without diluting which are coarse-grained non-reactive material. So large hydraulic conductivity. So when we will experience large hydraulic conductivity, when there is a small small pore size. So, so whatever the PRB which is prepared with bone char phosphate is what they are saying is allows its use in PRB without dilution with coarse grained non-reactive material. So in case of bone chalk phosphate, there is no need of adding coarse grained particles to synthesize to prepare these PRBs because of it has large hydraulic conductivity. If it is permeability high is higher, we don't need to. If permeability is higher, there is no much force to remove this small particle in the PRBs. Again, when it comes to the conclusions, some conclusions and results. So AFOs mixed with 3 by 8 inch of gravel may we can choose this material, only some materials, mainly AFOs mixed with 3 by 8 inch gravel, means presenting 2% of ferrous. And similarly Zircona zero valent iron form pellets. These two materials will be we can choose based on the results of batch and column test. So again in the results where in the results are showing that percentage of uranium removed in the phosphates and AFOs PRBs exceeded 70% for most measurements made during the first year of the operation. So the PRBs which is prepared with the phosphates and AFOs which show the more than 70% removal more than 70% uranium removal in the first year operation. But when it comes to the zero valent iron, it shows the highest uranium concentration removal more than 99%, 99.9% for a longer period of time. So because of this result, based on this result, we can conclude that so zero valent iron will be the best suitable best PRB to use it for removal of uranium concentration in that particular uh, contaminated site based on batch and column studies. We can conclude that. And then after that there is a discussion about configuration and potentiometry contours. So we already know the groundwater table contours levels will be different before we place the PRBs, like different contours will be different of groundwater flow, but when after installing the PRB the contour will be different. So we can see in the potentiometric contours will be changed before and after placing the PRB in the uh, field placing in the field. Again after that we saw the variation in pH and percentage uranium removal. So we chosen these three materials and we saw the uranium percentage removal with respect to different pH. So what we observe here is as pH increases the removal efficiency is decreases. So not only for particular material. So in most of the materials we saw the results. As pH is rises, the removal efficiency of uranium is less. And then uranium concentration in filtered and unfiltered water samples. So in that what will happen, we saw the comparison of uranium concentration in filtered and unfiltered water sample. So we see that higher pH zero valent iron in zero pH level in the zero valent iron will be higher. Zero valent PRBs will show higher pH because of, we already know that zero valent iron, what will happen when it reacts to water. So if any oxygen present in the groundwater, what will be the reaction? It is the zero valent iron is reduced to Fe2 plus, yes, and oxygen will get oxidized into hydroxide ions. So we know the pH, how if you see the pH form, what is the pH? It is the negative logarithmic of H plus ion. So as OH represent as presence of more H plus ions, more H plus ions, what will happen? There will be a reduction of pH. But presence of more H plus ion, it will show the rise in pH levels. Because of that rise in pH, it shows that alkalinity property. So because of this hydroxide ion concentration, so there is a higher pH level in the zero valent iron PRBs. If the PRBs, whatever the PRBs we used zero valent iron, so the pH will be raised because of this reaction. And then because of the main reason to raise this pH is because of the Fe not act as a reducing agent. So next, changes in dissolved oxygen concentration. So we saw the changes in dissolved oxygen concentration. So we saw the results in the graph. So the PRBs, which is made up of phosphates, which is having the higher oxygen concentration. But when it comes to the zero valent iron, there will be a there is no oxygen concentration or very minimal oxygen concentration. Because of why? Just before only we saw the reaction, right? So whatever the oxygen presented, it is oxidized into OH ions. Because of the, yeah, so OH ions, because of that we are not getting any dissolved oxygen concentration at the effluent of the PRBs. But when it comes to the PO4 PRB, we saw the more concentration of dissolved oxygen. And similarly, changes in oxidation reduction potential. So oxidation reduction potential, again, in terms of oxidation reduction potential, it shows the based on the reaction taking place between the reactant, and reactant nothing but the PRB media, whatever the media we are providing with help of PRB, and then the contaminants. So how well the reaction is taking place. So based on that, we see, if you see there is a more oxidation reduction potential for AFOs and then PO4. But when it comes to the zero valent iron, there will be a less oxidation reduction potential, because of this reducing condition are prevailed in case of zero valent iron, because of very less oxidation oxidation reduction potential in the case of zero valent iron. Again, in coming to the changes in ferrous ion concentration. Generally, changes in ferrous ion concentration will experience in only zero valent iron and AFOs PRBs, because in uh, in case of zero valent iron, what will happen again? So there will be a zero valent iron, it will convert into Fe2 plus. Again, it will convert into Fe3 plus, insoluble Fe3 plus. Because of that, there will be a change in concentration. There will be a change in concentration of ferrous ions. After whatever the Fe3 plus precipitated, it will after few years, once the PRP is completely there is no active sites to react with contaminants. What will happen? These precipitates will reacted Fe3 plus precipitates will come out effluent, and then it will result in showing the ferrous ion concentration at the downstream. Similar case with bone AFOs also. When you if you see the in AFOs, if you see the ferrous ion concentration, so again, so in ferrous ion concentration, with it in case of zero valent iron, in case of zero valent iron, the ferrous ion concentration will be uniform within the PRBs. Within the PRBs, it will be uniform. But when it is come to the upstream, it will be the ferrous ion concentration at upstream will be less. Only whatever the ferrous ion concentration which is there in the groundwater, those concentration will be shown in the upstream. But when it comes to the within the PRB, the concentration will be higher and uniform, because of reaction active sites will be there throughout the PRB, and the precipitation will take place through reaction will take place, and precipitation will take place throughout the RB. So we will experience the uniform and more number of more concentration, more and uniform concentration. But again, after in the downstream, we will experience lesser concentration. But over the period of time, also, we will experience very less concentration, because whatever even after complete blockage of these active sites, only few ferrous ion concentration will leach out from the membrane, not all. So we will experience very less concentration at the downstream as well, when it comes to the zero valent iron. But when it comes to the AFOs, when it comes to the AFOs, the upstream, again we see the uniform concentration throughout the even upstream, downstream. So even inside the PRP, so we will see the uniform concentration of ferrous ion. But in case of AFOs, we are not only looking for ferrous ion, we are looking for phosphate ion. But when it comes to the phosphate ion, similarly phosphate ions also, we will see the so when it comes to the ferrous ion, we will see the uniform concentration at downstream, upstream, and within the PRB. But when it comes to the phosphate ion, we will see the uniform phosphate ion, because the PRB is prepared with the phosphate ion, So the within the PRB the phosphate ion concentration will be higher, but upstream will be lower, because whatever the phosphate concentration will be there in the water, groundwater only will see, and after in the downstream also we will see the less concentration. Only within the PRB we will see the high concentration. And then we here they discuss briefly about annual cost, duration and of project planning, that is mainly referring to the PRB which is installed at Utah in the USA. And then conclusion about PRBs. So if you see the conclusion, the PRBs are the efficient and financially viable means of remediating uranium contaminated groundwater. So these PRBs not only remediate the uranium contaminants, it also other it also remediates the other contaminants too. So the results of this project have been widely applicable. They were saying whatever the results they are getting through that particular contaminated site, which is at Utah in the USA, that results can be there. They are saying it can be widely applicable. And then next topic is, that is important topic. So attenuation, natural attenuation. So what is the natural attenuation? So there will be we can remediate the contaminate site without installing the PRBs. There will be a natural forces which can drive in remediating any contaminant, but not up to the with great with not with great efficiency of removal compared to PRBs. PRBs will show very great removal efficiency within shorter period of time, but when it comes to the natural attenuation, it will show very less uh, reducing the very less concentration. So again, in natural attenuation we have different mechanism. One is non-destructive mechanism and second one is destructive mechanism. So in natural non-destructive mechanism, what we will observe, there is no change in concentration, just concentration will shift from one place to another place, or in the form of different mechanism, like one is sorption or dispersion or diffusion or dilution or volatilization. So in volatilization what will happen, in case of I am discussing about only currently I am now discussing about only non-destructive mechanisms. In non-destructive mechanism, the concentration of contaminant will be reduced because of volatilization. Volatilization nothing but at particular temperature or something. So the whatever the contaminants will change the phase from the liquid to gaseous phase. Because of the changes of phase, the concentration of the contaminant will be reduced. So this is the, but concentration is not removed completely, because it's just shifting the concentration from liquid phase to the gaseous phase, but overall mass of concentration will be remain same in the environment, but some portion will be remain in water, some portion is changed to the gaseous phase because of this volatilization. Sometimes similarly with sorption. So first mechanism is sorption. In sorption what will happen, so some organic contaminant will be absorbed some contaminants will be absorbed on the organic fraction of the organic fraction of soil. Because of that we will see reduction of concentration of uranium or any other contaminant because of the sorption. But it doesn't mean it's not removing, just it is transferring the concentration from one place to one another place, or just shifting the phase. And then second, coming to the dispersion or diffusion. So once the particle some mole of contaminant, so traveling through different soil strata. So these 3 mole of contaminant will be traveling can be traveling different paths. So travel of this contaminant in different path, if same mole of contaminant travel in different phases, whatever the concentration of the same contaminant will be different in different destination because of their dispersion and diffusion. Because of that we can see the reduction in concentration. And similarly dilution. So we discuss about dispersion. And then dilution, what will happen, just combining a small portion of contaminate, for suppose 10 milligram of 10 milligram of contaminant in 1 liter of water will be this concentration. Same concentration, 10 milligram of concentration is diluted with another 2 liter. What will happen, that will be 5 milligram of 5 milligram per liter. So the concentration is completely reduced to 50% because of the dilution, addition of another extra liter of water. So what will happen, the contaminant concentration will be can be reduced due to the dilution as well. Similarly volatilization I discussed. Volatilization, because of changing the contaminants will change from the one phase to another phase, mainly liquid phase to the gaseous phase. Because of that we'll see we'll see the reduction of contaminant concentration. These 4 mechanisms are belongs to non-destructive attenuation. So coming to the destructive attenuation, in destructive attenuation we'll see the, in non-destructive attenuation we will see the just we don't the concentration will not degrade, the concentration will not reduce, it is reduced because of shifting concentration from one place to another place or one phase to another phase. But when it comes to the destructive attenuation, the concentration will be reduced because of the natural reactions, whether it may be due to the microbes present in the groundwater. Such we will discuss different mechanism in the destructive attenuation. So in destructive attenuation, what we see, the mass and concentration attenuation also we can see. So here we have one mechanism is biodegradation. So the biodegradation, the name itself representing that the degradation of contamination is taking place with the help of microbes. Again there will be a degradation in biodegradation in biodegradation there will be a 2 mechanism, that is, one is anaerobic and aerobic. So in aerobic what will happen, there we will see the presence of oxygen in the aerobic condition. So this oxygen act as an electron acceptor, and then whatever the contaminant will act as a electron donor. Once there will be electron acceptor and donor, the reaction will take place, right? Again after the end of the every chemical reaction, what will happen, there will be some release of energy. So this release energy will taken by these microbes to for synthesis of for synthesis purpose. And when it comes to the anaerobic, what will happen, there is no presence of oxygen in anaerobic so yes, so in anaerobic, there will be absence of oxygen. So if there is no oxygen, nothing means there is no electron acceptor. So in this case, what will happen? We need electron acceptor. Already electron donor is there in the form of contaminant. But here, what will happen? Mainly this whatever the chlorinated solvent, this oxidized compound we can it can be used as an electron acceptor and to remediate the any contaminant. Again we saw some biotic degradation, biotic and abiotic degradation, mainly because of that reductive dechlorination and hydrolysis in the presence of water. And then naturally occurring bioremediation. Naturally occurring bioremediation, as we discussed, naturally occurring mainly due to the microbes present in the contaminated site or in the groundwater. So again, naturally attenuation we also call it as an intrinsic bioremediation, also we can call. The results of metabolic activity of microbes need energy for growth of cell synthesis. So what at the end of when there is electron acceptor and electron donor, then reaction will take place. Whatever the energy released from through that reaction, that energy will be utilized by the microbes for their cell synthesis. But the disadvantage in this case is the kinetics. The reaction will take place very slowly. So because of that, very less number of very less concentration will be reduced. So main drawback in this natural, yes, of course there is cheaper, there is no treatment equipment, nothing is required, but there is a, it is very slow process. So there is again it is slow, kinetics will be slow, and at the same time it won't completely degrade the all the contaminant. So degradation will be incomplete. Only few, particular microbe cells will be best suitable to remove to degrade particular contaminant, but some microbes won't show any degradation to some contaminants. So because of that, what will happen? So there is no complete degradation of contaminants. So these are the main drawbacks in the naturally occurring bioremediation. Again, biostimulation. So in biostimulation, what we are going to do? So we are adding addition of relevant accident or reductant to increase the bioavailability within the medium. So what we are doing, we are whatever the to make any biodegradation, we need electron donor and electron acceptor. So again, in other than electron acceptor or electron donor, for growth of microbes, what they need nutrients, and then uh, environment, surrounding environment such as temperature and pH of that particular, we have to maintain optimum condition to grow the to maintain the proper growth of microbes, so that biodegradation will take place rapidly. Or the kinetics will see the some uh, rapid kinetics in the biodegradation. So for that, we have to maintain the nutrients, pH and temperature and oxidation, oxidant or reducting agents. So we can enhance stimulate nothing but increasing the kinetics. So increasing kinetics nothing but we are just promoting, we are providing conditions such a way that to promote the growth of microorganism. So what we do, how can we promote? By providing this growth condition to the microorganism. What are the things needed? One is whatever the electron donor acceptor, right? So for electron donor we did accident and acceptors for reductants and nutrients, pH, oxygen, temperature. If you maintain this part, all these parameters, uh, uh, if you maintain this all these parameters, the we'll see the uh, very rapid growth of microbes. So once there will be growth of microbes, what will happen? There will be a natural degradation will take place. So how can we add oxygen? Like, so if there is any contaminated groundwater is there, so we can add. artificially pump the air. If in most of the cases groundwater will be just below the soil strata, so it is most of the case it is a unconfined condition, so there is will be very less presence of oxygen. So to supply oxygen to promote the growth of microorganism, what can we do? By using blowers we can directly supply the air to the groundwater to promote the microbes. And then coming to the bioaugmentation. So what is bioaugmentation means? So addition of matched microbe strains to the medium to enhance to resident microbes population ability to break down the contaminants. So what we'll do, if because it is very difficult to provide optimum conditions for microbial growth, it is very difficult to maintain this whatever the pH and temperature and nutrient levels and electron acceptor donors and electron acceptor nothing but oxygen, so it is very difficult to provide inside the groundwater. So what we'll do, what in this situation what can we do? So in this situation what can we do? We can uh, we can promote the growth of microbes at any other place, so which is suitable, which is there suitable where we can find the suitable condition for uh, microbe growth. There we can cultivate the microbes, and then we'll shift the same microbial strain to the contaminated side where it requires to degrade the contaminant. So in the way in this mechanism we called it as a bioaugmentation. And then evaluation of naturally occurring bioremediation. So mainly advantages and disadvantages we will discuss. What are the advantages of bioremediation? So one is it is low cost and can be applied to all parts of sites. So in case of PRBs, we can't apply install the PRB throughout the contaminated site. We can install only particular site, so where we'll see the based on the contour line and flow path we can install this PRB at particular place. So we can't install the PRB whole contaminated at any whole area of contaminated site, right? So but when it comes to the natural biodegradation, uh, we can bring these microbes to any place of contaminated site to reduce the concentration of contaminants. So you can apply it in all parts of this contaminated site. And that too, remediation degrades also it degrades the contaminants as PRBs do, but compared to PRBs it will the reaction will be, the kinetics will be very slow, and there is no above structures needed for treating the contaminated site. But when it comes to the disadvantage of biodegradation, there is a very less very slow kinetics will see, and incomplete degradation, long time required, and very long time required to degrade the contaminants, that too very few uh, few contaminants, and then long term monitoring required. So extensive site characterization, because we can apply this bioremediation can be whole part of the site, so at the same time we need extensive site characterization. So site condition can change such that not suitable for natural attenuation. So because site conditions are different from place to place throughout the contaminated, we can't see the same level of pH, dissolved oxygen, and other nutrients level and microbes. So such condition in some places we will experience that we can't see any microbe growth in that particular places. So in this case we can there is it is in this particular case what can we see, it that particular place will not suitable for natural degradation because microbes are not growing there. Again, mechanism of biodegradation mechanism we already discussed in aerobic process, what will happen? Oxygen act as a electron acceptor, an organic compound act as a electronic donor, and reaction will take place, and whatever the energy released in the reaction taken by the microbes for cell synthesis. In anaerobic process, in the absence of oxygen, if in the absence of oxygen, some other elements act as a many other compounds are there in the groundwater or contaminated site, which can act as a electron acceptor when there is no presence of oxygen. Those compounds I am writing down. One is nitrate, because it is electronegative compound, can act as a electron acceptor. Nitrate and nitrite both can act as a electron acceptor. Similarly, if we replace sulfur dioxide, CO2 minus, chlorine compounds. So these compounds can be act as a electron acceptor when there is absence of oxygen. When there is a presence of oxygen, automatically oxygen will be act as a electron acceptor, because of in the presence of oxygen we'll see the more release of energy, because uh, whatever the electron accepting what microbes will accept the electron in the reaction, which releases the more energy. So of course in case of oxygen, the release of energy will see more higher. Then that's why we are in the presence of oxygen, these microbes utilize as a oxygen as a electron acceptor. But when in the presence of oxygen, based on their energy release capacity, microbes choose any one of these compound as a electron acceptor mainly in the anaerobic process. Similarly, we discuss about fermentation. So fermentation, nothing but organic compound can be react with more oxidization form or more reduced form. Suppose if we see the reaction like CH3COOH, CO2 will be more oxidization in the form, and CH4 is more reduced in the form. So that is called fermentation. So we discuss briefly about week 5 content. Now we'll move to the previous year questions. We'll solve some previous year questions. Okay. Yes. Yes. In non-destructive, how can you asking how can we conclude in non-destructive mechanism there is no change in concentration? Yeah. So for suppose, see, I'll pick any one mechanism. For suppose dilution. Dilution is one mechanism in the non-destructive, right? So for suppose you assume that there is a water. Uh, the uranium concentration in this water is 10 milligram per liter. So there is a 1 liter of water, and then uranium present in this 1 liter of water is 10 milligram. The concentration will be concentration of uranium is 10 milligram per liter, right? So now what I am doing, to the same bottle or same area, what I am doing, I am adding uh, one more liter water. Without it doesn't, this water, 1 liter water doesn't have any uranium concentration in it, but the uranium concentration is there in only this tub. But whatever the water I am adding to this tub is 1 liter, but the concentration of uranium in this water is 0 milligram per liter. Now I added this 1 liter water. Now it became, so the how will did you expect any same concentration or change in concentration? Same concentration. So okay, now I'll explain you. So here uranium concentration is 0 condition, that is 1 liter. Now in this is case 1. This is case 2. Uranium concentration is 10 milligram and water is 1 liter only. So now I mixed these two, case 1 and case 2 liquid. The whatever the mixed concentration, how we will find mixed concentration? Yeah, no, not C1 C1. See, now volume, whatever the volume there at case 1, that is V1, and concentration present at V1, that is C1, plus, and case 2 volume at case 2, that is V2, and concentration at case 2, that is C2, by total volume. Total volume nothing but total volume at case 1 and case 2, so that is V1 plus V2, right? So now you calculate the mix. So V1 is how much? V1, that is 1 liter. C1 is 0 because, right, and V2 is 1 liter and C1 is 10 milligram per liter, sorry, C2 is 10 milligram per liter, and V1 is again 1 liter and V2 is 1 liter. Now calculate the mixed concentration, that is 1 into 0, that is 0, 0 plus 10 by 2. What will what happen? Yeah, right, it is reduced. So but there is no degradation take place, but the concentration is reduced, right, because of the dilution. Now you got the point. Yeah, so similar case, if you see the volatility also one another mechanism, right? So in this case what happened, first of all 10 milligram of uh, hydrocarbons, I can say petroleum hydrocarbons. So in the groundwater, 10 milligram of petroleum hydrocarbon concentration is there. Because of these hydrocarbons are highly volatile, what will happen when there is a rise in temperature or such conditions, change in pH condition, some portion of uh, volatile carbon compound will change its phase from liquid to gaseous. Here suppose 5 milligram per liter changed to gaseous phase, and remaining 5 will be there in groundwater itself. Now there the whole concentration will be 10 milligram only, but 5 milligram per liter is in liquid phase, 5 milligram per liter is in gaseous phase. So in this way we can say that in non-destructive mechanism, the change in concentration will be reduced because of from shifting one place to another place, or from moving one place to another place, like, or either because of diluting. But in case of destructive attenuation, what happening, these microbes are completely taking up this contaminant and completely degrading. but there is some restriction. Yeah, now I think you got the point, like how it is reducing. Now we will see some few previous year assignment questions. So in previous year week 5 assignments, so the first question is groundwater at a site is contaminated with uranium, a radioactive compound. Actually uranium is a radioactive compound, we know. Which one of the following technique shall not be considered for remediation of the contaminated site? So they are asking, there is a one site which is contaminated with groundwater is contaminated with uranium, and then they are asking which of the following remediation technique we should not consider for remediating uranium. So one is they are saying solidification and stabilization. It is solidification, stabilization, nothing but you can say precipitation, and monitoring the natural attenuation, and second one is pump and treat, and third one is PRBs, permeable reactive barriers. So yeah, pump and treat we should not consider. Why? Because yeah, so it is radioactive material. If you take it out this contaminated groundwater which is having radioactive compounds, so what will happen, it can be exposed to the natural na surrounding environment, either humans beings or animals or any habitat. So it will be react danger, as well as pump and treat method we need above structure construction, which is very highly costly affair. So again, it pump and treat is the not best suitable technique to treat the uranium in the groundwater. So the option answer for this question is C. Pump and treat is not we should not consider pump and treat as a best technique to treat to contaminate the groundwater which is contaminated with uranium. And then second question, the material used in PRB should have dash porosity compared to the porosity of surrounding aquifer material. More porous, right? Because so if the PRB, for suppose PRB has less porous than the surrounding material, what will happen, flow will take place to this to through higher permeability area. So but we wanted to pass water through the PRB to treat the contaminant, so we should make sure that PRB's permeability should higher than porosity, nothing but if there is higher porosity, the permeability higher. So we should make sure that porous PRB's PRB's porosity higher than the surrounding strata, so that we can remove the contaminant from the contaminant side effectively. Answer for this question is B. Okay, and then third question, we can employ PRB as a remediation method when the contaminant is a radioactive compound, B is contaminant plume spread over a large area and the plume shape is unclear, and C is the contaminated plume is confined to a small area, and D is all the above. So in which case we can employ the PRP method? So yes, first option is right. The contaminant is radioactive compound. Any other option which can be suitable for PRBs? The the contaminated plume is confined to a small area. Yes. So if there is a contaminated area spread or contaminated plume spread over larger area, it is very difficult to install PRBs. Again, they are saying the shape plume of the shape is unclear. If we don't know the plume shape, we can't install. We don't know where to place the PRB. So we can't choose. We can't apply the PRB in this B case. So, but we can apply the PRB in case of the contaminant is radioactive compound. Yes, the contaminated plume is confined into small area. So in this two case we can apply the PRB. So answer for this question is A and C. Fourth question. Which of the following process are example of non-destructive attenuation? Which of the following process are example of non-destructive attenuation? Just before only we talked about destructive, non-destructive, right? So in non-destructive attenuation, which of the following process are example of non-destructive attenuation? One is advection, biodegradation, dispersion, volatilization. So advection comes to the comes under destructive or non-destructive? Non-destructive. And similarly, biodegradation, yes, biodegradation destructive, so no. And dispersion is non-destructive, and volatilization is non-destructive. The answer for this question is A, C, D. Nice, good. So which of the following question number 5, which of the following statements is not true? So the statement one is bioaugmentation refers to addition of microbes to promote the biodegradation. Is this statement is true? Yes, statement A is true. And second statement, the breakdown of compound into its more oxidized and reduced form is called fermentation. The breakdown of compound into more oxidized and reduced form is called fermentation. At the end of this overview of week 5 section, we discuss fermentation, right? So organic compound, mainly the CH3, yeah, exactly right. So is this statement true or false? True. Statement B also true. Now statement 3. Dispersion is the bulk movement of the fluid in a particular direction. Is this statement is true? Dispersion of a fluid in the dispersion is the bulk movement of fluid in a particular direction. So dispersion itself we represent it as a moving the flow in a different directions. Like a single compound can move in different this direction or this direction, in this direction also. But what they are saying, dispersion means moving in a particular direction. So is this statement true or false? Yes, statement C is false. And then question D. So bioventing is adding oxygen into vadose zone to promote the biodegradation. Vadose zone nothing but anaerobic zone, you can say, right? Okay, bioventing is addition of oxygen into anaerobic zone to promote the to promote the biodegradation. Is it statement is true or false? Yes, true. So answer for this question is C. So which of the following statement is not true? They are saying. So A, B, and D are true, and C is false. So answer for this question number 5 is C. Question number 6. So groundwater sample at location at two locations A and B as shown in the figure. So groundwater sampled. So groundwater as sampled at two locations by pumping. So A and B, flow direction from the A to B. So observation, they are observed that contaminant called ciprofloxacin. Ciprofloxacin, an antibiotic, was found in both samples. Okay, they found this contaminant called ciprofloxacin in both observation were A and B. Second observation is the concentration of ciprofloxacin was found to be less in the sample B than the sample A. Sample B, they are saying CIP concentration will be less at B, higher at A. So now they are saying what are the possible reasons for the above observation. So what are the possible reasons to reduce the concentration from the B to A? So what could be the reasons? So we'll see dilution due to advection in the direction of groundwater flow, sorption of some amount of CIP onto the soil between A and B, and biodegradation of CIP between A and B. So what is the answer? Yes, all of the above, because in between these 2 points observation where these three mechanisms can take place, either both destructive or non-destructive mechanism can take place. And question number 7. Question number 7. So sorption of compound retards the mass transport of compound in the subsurface. Sorption of a compound retards the mass transport of the compound in the subsurface. Is this statement is true or false? Yeah, below the ground level, subsurface means. Yes, of course it is true, because of the sorption, what will happen? Adsorption will take place onto the soil, which is there in subsurface level soil strata, which absorbing the some mass concentration of contaminant, which is transporting through this groundwater. Because of that, what will happen? Retardation means transport. It will reduce flow, mass transport from the one place to another place because of the sorption of that particular compound and the substrate strata. So statement is true. The question number 8. With reference to the concept of completing electron acceptor, select the correct sequence of preferred electron acceptor for the microbes. So we discussed, right? So in the presence of oxygen, the more microorganism will take place oxygen as a electron acceptor, because of it presence of oxygen will release the more energy in the reaction. So these higher energy, release of higher energy will taken by the microbes, and it will be utilized for cell synthesis, for their own cell synthesis. So, and then in the presence of oxygen, we discussed nitrates or nitrites, and SO4 and RCl. So they are asking that with reference to concept of completing electron acceptor, select the correct sequence of preferred electron acceptor for microbes. So what will be the answer? B, right, because in the presence of oxygen, automatically the microbe will take consider oxygen as a electron acceptor first preference because of it, because in the presence of oxygen the energy release will be higher in the reaction, right, in the product end. But after that NO3 will be released higher energy compared to SO3. After SO3 uh, energy SO3 SO sorry SO4 sulfate. So so SO4 release higher energy compared to chlorine compound. So at the end chlorine compound will release a lesser energy. Hence microbes choose RCl at least preference because of its less release of energy. So option for question number 8 is B. Right answer is B. So last question. Limitation of monitored natural attenuation include. Limitation of monitored natural attenuation include cost consideration, slow kinetics, change in site conditions over a long period, no above surface structure. Limitation nothing but you can consider as a disadvantages. Yeah. So what are the disadvantages in the natural attenuation? Yeah, slow kinetics one is. Change in site condition over the long period. Yes, right. So good, very good. So yeah, we are done with all the questions, previous year questions. So Nirupa, you answered all the questions very good. So if you have any doubts, I will be staying in online for 10 more minutes. If you have any doubts, you can ask me. Okay, thank you. Yeah, you can leave.